All right, here we go. And as you can plainly see out the window, the storm they've been talking about is in the works. So I hope you've gotten everything done you needed to do. It doesn't look good out there, does it? So, all right, anyway. So here's what we're going to do today. Let's go to Moodle, and we'll find over there Chapter 5, problem set number 2. So we'll go through this. And when it's done, we'll wrap up Chapter 5, the third part of Chapter 5, which is 5C. And maybe if there's time, take a peek at 6. So therefore, let's get started with this. And so while there's a lot of questions on here, they're all fairly short. So this won't take up the whole period by any means. And so you can see a lot of them involve radicals. So why don't we begin right here? And let's start with the beginning. All right, hold on. What the hell is going on? All right, it's being stubborn. Hold on one second. Let's try that again. There we go. All right, it's ready. Okay, so we'll start with the square root of 49. So we'll note here that since 49 is a perfect square, the square root of 49 must be rational. Okay, and of course you could also note that the square root of 49 is 7, which is of course a rational number because it's an integer. All right, but on the other hand, if you look at number 2, since 37 is not a perfect square, the square root of 37 must be irrational. And that's all we have to remember. Perfect squares, the square root is rational rather. Anything else, the square root is irrational. All right, very good. How about this one? Now, if you don't look at this carefully enough, you may think at first glance that it is a repeating decimal, but in fact it's not, because if you notice it starts with 0.23 and then it goes on to 0.233 and 0.2333. So yeah, since this is neither, or this is not a terminating decimal, and it is not a repeating decimal, it is irrational. All right, we're not going to be able to find a ratio of integers that equals this number. Okay, it doesn't exist. All right, now let's see what's next. Oh, well, this one is pretty open and closed. Is 5/6 rational or irrational? Since this is the ratio of two integers, it is rational. Okay, because that's what rational actually means. So that one is pretty open and shut. Now this one, you already know that pi is irrational. We're not going to attempt to prove it here, but we know that pi is irrational because there is no ratio of integers that can give us back this number. And you know, mathematicians have been spending centuries looking for it, but it doesn't apparently exist. I don't know if anyone's ever come up with a proof that it can't be rational, but for sure they've never found a ratio that works for this. Very well. Now, 0 is considered to be irrational because it can be expressed as the ratio of two integers, such as, for example, 0/1, 0/2, etc. And of course, 0 is an integer. So therefore, these ratios show that 0 is a rational number. So like all the other rational numbers, there's an infinite number of ratios we can construct of integers that give us back 0, all of them with 0 in the numerator. Okay, so there's no problem there. Here we go. Now it's time for simplifications. Now we all know and love simplifications. It's just fun, isn't it? Simplifying radicals is a fun game that we can play. And of course, remember the idea here is just to get it as simple as possible. Sometimes it's not possible to simplify it. So for example, what do we do with this one? All right, what we should try to do in all these cases is try to find the factors of 24 where hopefully at least one of them is a perfect square, if they exist. If not, well, then there's not much we can do about it. But here is an example where we have 4 times 6. And this breaks down into radical 4 times radical 6, which in turn becomes, 2 radical 6. And now we can't go any further because 6 cannot be broken down into any factors which contain a perfect square. Okay, in fact, all we have here is 1 and 6 and 2 and 3. And none of those can be used to simplify any further. So this is the final result. All right, now how about this next one? 27, what can we do with that one? Let's think about this one. If you write out all the factors of 27, you'll discover pretty quickly that we have 9 times 3. That works out well because that gives us back 3 radical 3. And we're done. That's as simple as we can get it. Okay, how about 680? What can we do with that one? Well, there's more than one way of getting this one simplified. So the one that I like the best is this one because this involves the fewest steps. You can rewrite this as 16 times 5. Now, you could also have written it as 4 times 20 because 4, of course, is a perfect square, but you would still need to go through extra steps. So anytime we have a number like this with more than one factor, which is a perfect square, your best bet is to pick the highest perfect square that you can find. And that will simply minimize the amount of work that you have to do. But look how simple this one is. And then we're done because, of course, 5 is a prime number. It cannot be, the square root will not be any simpler. We just have to leave it like this. All right. So how about this one? Now, you might look at it and say, well, I don't see any perfect squares in there. Yes, you do. You just didn't realize it. This is equal to 25 times 7. Okay. Oh, yeah, there you go. Now that I've showed it to you, now you're like, oh, of course, it's 25 times 7. All right. So we end up with 5 radical 7. Of course, we can't go any further because 7 is a prime number. All right. So you all recognize that right away, 25 times 7? Good. All right, that's good to know. But sometimes it's not so obvious, is it? Now 30, let's take a closer look at 30. What are the factors of 30? Oh, this one doesn't look promising, does it? Yeah, those are indeed, but are any of those prime perfect squares? No. Oh, we left one out, 5 and 6. No. How discouraging. How depressing. Yes, those are the factors, but guess what? There's no perfect square, so guess what? You can just leave it. Okay, so when it says simplified, you can write your answer as radical 30 because that's as simple as it's going to get. And you can see it happens. There's no guarantee that we can simplify these radicals. It just, that's how it is. Not every radical can be simplified. Now let's look at 42. Ooh, now you would think that this one would have some perfect squares as factors. Let's find out. 1 times 42, 2 times 21, 7 and 6. Okay. Oh no. Do you see any perfect squares in there? No. So we're done once again. Oh well. And what are you going to do? Now, these are a little different because there's a constant involved that we didn't have here. And so even though sometimes you may not be able to simplify just the radical, but when you have this constant here, that might change our results a little bit. So let's see what happens here. Oh, here we go. Wait a minute. This one has exactly what we're looking for. One of its factors is a perfect square. So it's 10 times 2 times radical 5. Ah, look at that. 20 radical 5. That's a nice, by radical standards, that's a nice number. Okay. It's not as nice as 5, but let's say that's pretty simple. That's as simple as we're going to get it. Okay, now let's try this one. Well, now that we're getting pretty good at this stuff, it should be pretty clear that this is 4 times 2 under the square root sign. Ah, look at that, how nicely that reduces to 8 radical 2. Okay, and we're done. Now look what we have here. Ooh, I like this one because look how easy this is. Yeah, this is our favorite perfect square, isn't it? 100? I bet it is. Because everybody knows and loves 100. Now the square root of 100 is of course 10. And so we end up with 30 radical 7. Nice. Oops. Let me fix that. Yeah, so that is the final answer, 30 radical 7. 7 is prime, and we can't go any further with it. Now, here's an interesting one. It's 2 radical 162. What are we supposed to do with radical 162? Let's think about the factors of 162. Well, of course, we don't need to bother with 1 and 162. Oh, wait a minute. What do we have here? A perfect square. Boy, how lucky did we get today? So that ends up 18 radical 2. Okay, 81 is, of course, the square of 9. And so that one simplifies very nicely to 18 radical 2. All right, good work. Now, let's see. Are we coming up on any strange ones? Well, now we're going to start doing some algebra. But we're still always trying to simplify whenever possible. All right, just because we're multiplying doesn't mean we stop trying to simplify. So what happens here is that each one of these individually cannot be simplified, but yet when we multiply them together, look what happens. Oh yeah, look at that. Well, that worked out nicely. We got 2 radicals that could not have been simplified. Suddenly their product, it can be simplified. How do you like that? And the same thing will happen here. We cannot simplify either of these separately, but when we bring them together, 90. Now we know what to do with that. So the final result here is 3 radical 10. Yes. Now we'll look at this one. 18, radical 18 times radical 15. That turns out to be radical 270. I wonder if there's any perfect squares that are factors of 270. Well, 2 and 135 doesn't seem to help. Oh, here we go. See, now 3 and 90 by itself is not that helpful, but this implies that we have 9 times 30. And that's what we're after. So let's rewrite this as radical 9 times 30. Now, we already proved earlier that radical 30 can't be simplified. So we're done. Wow, that was interesting. Now, this one, we can actually approach it in 2 different ways. You can start by saying, well, you know, this is the square root of 125, which is in turn the square root of 25 times 5. But you know what? This actually wasn't absolutely necessary because all we had to do is recognize this is just 5. So we could have just said, oh, well, then this is just radical 5 times 5, which you would normally write as 5 radical 5. And guess what? It's the same thing. Of course it is. So in that case, multiplying it out wasn't absolutely necessary. We could have gone directly to here and you would have gotten the same answer. All right. So now in the next group, we're going to multiply, but now in each case, there's a coefficient in front of the square root sign, which, you know, complicates things a little bit. Just a little. We have to remind ourselves that when you're doing this, you can rewrite this as 2 times 3. And then you can multiply these together. Okay. So this is 6 radical 48. Now here we get a break because 48 is 16 times 3. Oh, yeah. So you get 6 times 4 radical 3. 24 radical 3. Much nicer than what we started out with. Look at this mess. Yeah, that's so much better. Okay, so now let's see, what about this one? So we'll multiply the constants. And the radicals. So we'll have 12 radical 75. Oh, look at this. That 75, guess what it has as a factor? 25 times 3. So you got 12 times 5 radical 3. 60 radical 3 is our final result. Very pleasing to the eye, would you agree? In fact, if you're an arts major, you might be tempted to make a painting of 60 radical 3 just because it's so cool to look at. Oh, you can make it all, very bizarre and abstract looking, but that's the center of the painting. And everyone will look at it and say, what are you trying to tell us here with this? And you can maybe sell it in a gallery in the village for $1,000. Who knows? Okay. Now, these are, of course, ratios. And sometimes this will help us simplify things. So let's try this. Oh, look at this. Our old nemesis, radical 30, is back. There's nothing we can do with it. That's going to haunt your dreams tonight, isn't it? Radical 30? Yes, it is. By now, you've started to having dreams about math already, right? I mean, isn't this normal in the beginning of a math semester that you become so obsessed with it that you start dreaming about it? I bet you have. You just don't want to admit it. So anyway, there you go. Now look at this one. Okay, this is easy because it's just radical 7. 7 is prime, and so we're done. Okay, now, how about this one? So when you combine them into a single expression, so it's radical 8, but we're not done because this is 4 times 2. And so we end up with a much nicer result, which is 2 radical 2. And then this one, we know what's going to happen here. It becomes radical 5, which is it's prime. We can't do anything with it. All right, now here we're going to try to add and subtract these radicals. And note that here, because these are both radical 7, we can certainly go ahead and add them up. This is what we're actually doing. We're combining these, and we end up with 12 radical 7. Same thing here. We got the same radical, so we can just rewrite this as 50 plus 11 times 11. And that's all you have to do. There's no simplification because 11 is, of course, a prime number. Now, this one is a subtraction, but of course, it follows the same rules as addition. You can only do this because these are the same radicals. You've got 8 minus 15 times radical 3 or minus 7 radical 3. Okay. Now, these are interesting. Look at these. Now, if you look at this one, you might say to yourself, wait a minute, doesn't this break the rules? I can't add these together. I can't subtract them. They're not the same radical. But that's not necessarily true because watch what I can do. Both of these can be have a common factor of 5, as it turns out. So in other words, this first one could be rewritten as 64 times 5. And this one can be written as 16 times 5. So now things are looking a lot more promising, aren't they? Because, ooh, look at this. And in fact, we were able to combine them into one new expression, which is clearly simpler than what we started out with. So in other words, even though it wasn't immediately obvious, we were able to ultimately to combine them because we were able to rewrite them in terms of a common radical. Now, maybe something like that will happen here. Let's try this. Do they have a common factor of 5? Yes. Well, well, well. Look at this. Whoops. There we go. Okay. Five radical 5 plus 2 radical 5. They add up to 7 radical 5. And of course, we can't go any further because the 5 is prime. All right. Okay, there's just a few more. Let's see, what else do we have waiting for us here? How about this one? Well, it looks like they have a common factor here because I know that 80 can be written as 16 times 5. So I've got 6 radical 5 minus 3 times radical 16 times radical 5. So I end up ultimately with 6 radical 5 minus 12 radical 5 and the final result is negative 6 radical 5. Nice. How about this one? Ooh, I know. It looks pretty obvious that these both have a common factor of 10. So we're going to have 13 radical 9 radical 10 plus 5 radical 4 radical 10. 13 times 3 radical 10 plus 5 times 2 radical 10 is 39 radical 10 plus 10 radical 10. And finally, I end up with 49 radical 10. And that's it. I can't do anything with 10. The factors are 1, 2, 5, and 10, none of which helps me. Okay. Very good. So now we're going to rationalize the denominator, which means we're trying to get rid of that pesky radical in the denominator. Now, here's what you normally do. Of course, you're all aware that you're allowed to multiply any number by 1 without changing its value. And we're going to do that right now. But I'm going to pick a very special form of 1. how about radical 5 over radical 5? How does that help me? Because I get rid of the radical in the denominator, and that's all I need. I can't simplify it anymore because 5 is a prime number. Now, how about this one? So in these cases, you always take whatever's in the denominator here and multiply by the ratio of that number to itself. So I have 3 radical 8 over 8. Now, you might think we're done, but you'd be wrong because look what you can do now. 8 is 4 times 2. Okay, and let's say that, that can now give us 3 times 2 radical 2 over 8, 6 radical 2 over 8, and finally, when we're done, when all the dust settles, this is our final result. We obviously can't go any further because 2 is a prime number. All right, what else do we have here? Ooh, let's take a look at this one. So we're going to take our 3 over radical 6, and of course we'll multiply it by radical 6 over radical 6. And this one simplifies a little, and that's it. No more. No more simplification for us. All right, now we're going to do the same thing for this one. All right, well, you all know how this works now. So I've got 10 radical 20 over 20. So the 20, radical 20 is actually 4 times 5. And let's see, that of course becomes 10 times 2 radical 5 over 20. And that just reduces to radical 5. How do you like that? That was pretty satisfying, don't you think? Yeah, this mess turned into this. Okay. Now these are different now. Here we're not rationalized. Well, we are and we aren't. But first we have to take one more step. In order to rationalize, oops. Oh, okay, that's fine. Yeah, and if you have to step out for a minute, that's fine too. Okay. All right. Now, what I was going to say here is that for this one, we should rewrite it like this first. 3 over 28 is this expression. Now we can rationalize it by multiplying both the numerator and the denominator by the square root of 28. So 3 times 28 is 84. So you might say, oh, that's all we can do, isn't it? But, oh, how wrong you would be. What can we do with 84? 84 looks pretty promising, doesn't it? Well, it turns out that it's equal to 4 times 21. Very good. So that's 2 radical 21 over 28. Or we can simply rewrite it as radical 21 over 14. Now this one is shockingly easy, watch. It's the ratio of 2 perfect squares. Oh my God, it's so easy. Now, it does say to rationalize it. I mean, if you did go ahead and rationalize it, it isn't really necessary in a case like this. You can certainly do it, but you're just going to wind up with 1 times 3 over 3 anyway. Sorry, 1 times 3 over 9. And you'll get 3/9, which is a third. But in a case like this, you can just go directly to here. Nice. Okay, one more. Now, what do we do with this one? And then we're going to multiply this by, of course, radical 3 over radical 3. And sadly enough, we can't go any further because obviously 6, it's not prime, but the only factors that it has are 1, 2, 3, and 6, and they cannot be simplified into a perfect square. Well, that was pretty exhausting, wasn't it? But man, we're really good now with this stuff. After all that, you're now experts in radicals and exponents and all the other good stuff we did. Okay? You're experts. I should give you a separate diploma just for that. I'll call the school and ask them if we can do that. Say, listen, don't just give them a diploma for graduating, give them a diploma for knowing how radicals work. You think they would like that idea? Oh, I don't know. They might not go along with that. You know what they'll tell me? They'll say, we have to get approval from the state of New York. That'll take about 5 years. And that would be the end of that. It will get lost in the bureaucracy. They have a math bureaucracy in Albany somewhere where their purpose of it is to lose everything. So anyway, so now we're ready to carry on with 5C. We just barely started talking about sequences. So that means it's time to do some more sequences. Okay, now we've already covered a large chunk of this chapter, but we're still not done with the last discussion, which is sequences. So if we recall, we said that there are 2 types of sequences, arithmetic and geometric. All right, so when we have any sequence, we have a series of terms, they're called, separated by a comma, which tells us that there is a pattern here. It's not like a set. A set can contain anything. Like if you had a set A equals 1, 2, 3, 4, 5, that just means that that's all that's in there and you're done. This is different. A sequence goes on forever, all the way up to infinity. And you can tell what comes next by looking at the pattern. All right, so that's the idea. It's a pattern. And so there's 2 ways this can happen. Well, there's 2 ways here. There are other ways, but we're only going to look at 2 of them. So we don't need this. So the 2 basic types are the arithmetic and the geometric sequences. There's plenty of others, but we're not going to do those in this class. Like the Fibonacci sequence clearly is much more complicated than what we're seeing here. It's a different kind of sequence. So the arithmetic sequences are the one where they have a constant difference between the terms. In other words, you're adding something to each term to get to the next one. So while they can start anywhere, here, for example, we have a common difference of 1, because how did I get from here to here to here? I keep adding 1. Here I have a common difference of 3, As you can tell, I've added 3 to each one. This one is a little trickier because the numbers are going down, but that just simply means I'm adding -1 to each term to get to the next term. All right, so now that we understand what an arithmetic sequence is, there are 2 things we may be asked to do. One of them is to find a particular term in that sequence. Now, you can always write them all out. Like if I needed to know the 20th term in one of these sequences, I certainly could write them all out because I understand the pattern, but that might not be very practical. It might be nice if we have a formula to do this for us. Formulas are good. They always help us get a lot of things done in a hurry. So let's take a look at the formula for finding a specific term in an arithmetic sequence. Here we go. Here's the formula. Now, remember, each term in a sequence is identified as A. Like here, for example, this is A1, this is A2, this is A3, A4, A5. That tells me what term I'm looking at. So the A has a subscript, which is here, whatever number it happens to be, that tells me which term it is. So this is the first term. Now, depending on what term I'm looking for, this is the term that I'm looking for, or we are looking for. This is the nth term, it's called, which we're looking for. And D is the common difference. So once you identify all these numbers, then all you have to do is plug them in. Okay. So for example, let's look at this one. So I'm putting this up here to remind you what this looks like. So we're given the sequence. Now you can tell that it's an arithmetic sequence because they have a common difference of 5. We're looking for the 10th term, so n is 10. And we also know that A1 is 1. So if we want to know the 10th term, here's all we have to do. 1 plus 10 minus 1 times 5 equals 1 plus 9 times 5 equals 46. And that's all you have to do. Now, what was the other option? You could have just written them out. You said, well, this one must be 26 and 31 and 36 and 41 and 46. So if you count them, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is A10 right here. You can see we must have done it correctly because that is in fact 46. Wow, I think now if you only have a few terms, maybe the formula isn't all that helpful. But if you're looking for, let's say, the 100th term, then that formula could save you an awful lot of time. Okay, so let's see if we got another example here. Oh, here's one. So your challenge is to figure out on your paper what is the 9th term in this particular sequence. All right, why don't you give this one a shot? Try to do it with the formula. You can confirm it by writing out the terms, but in this case, I would like you to also try the formula. All right, so let's give that a shot. All right. first, whoever gets there first, the prize is, I don't know. How about a virtual candy bar? How would that work? You would virtually enjoy eating it. I don't have any virtual candy bars to give you. So whoever gets there first, it's just for the pride of the thing, okay? The pride. So we got a couple of 34s. That sounds like it just might be the right answer. Let's see why. All right, so A1 is 2. 10, N is 10 because, 9, because we're looking for the ninth term. And the common difference, as you can see, is 4. Let me write that down here somewhere. Okay, so algebraically, we have 2 times, or 2 plus rather, 8 times 4, or 2 plus 32, 34. Perfect. And so let's write this out, and you'll see that, yes, you were absolutely correct. And this is indeed 1, 2, 3, 4, 5, 6, 7, 8, 9. This is the ninth term. Nice. So we have 2 prize winners in the game of, let's say, who has the best math skills, who has the biggest, who is the fastest. There's 2 people who are co-winners of that prize today. Okay. Now, sometimes we don't just want to know what terms we find in these sequences. It may be important to figure out the sum of the first n terms. Let's say, for example, you had something like this. Suppose I just want to know here's my sequence. What is the sum of the first 10 terms? Now, you can actually take out your calculator and add them up, but wouldn't it be nice if there was a formula? By the way, it's 55. I can do that fast because I know the trick. Either that or I must be a mathematical genius. No, there's a trick. It's 55. All right. So I'm going to show you the formula that will let you in on the trick. All right, here we go. Then you can use that to amaze your friends. You say, listen, just give me any sequence you want. I'll tell you in a matter of seconds what the sum is of the first n terms in my head. And they're going to say, oh my God, you must be a genius. You want your friends to think you're a genius, don't you? Doesn't that help? It changes the way they look at you, doesn't it? On the other hand, maybe they'd be afraid to hang around with you, so be careful. So, but anyway, willpower, that's right. In other words, whenever you have an idea, they'll go along with it because they think you're a genius. Like, I think we should do this. And they'll say, oh, you're the genius. We have to do what you say. Okay, anyway, here we go. So the formula is this. Now, it's a little bit trickier, but not too bad. So Sn means the sum of the first n terms. And of course, is the term that we're looking for, the first sum we are looking for, the sum of the first n terms. And then you know what A1 and AN are. This is the first term. And this is the nth term, as we've been calling it. It's a pretty straightforward formula to use, even though it looks a little frightening. So why don't we do some examples? And then I'll illustrate it with a very interesting anecdote from math history, which you might not think so, but math history is actually quite interesting. Very interesting. So anyway, here's our arithmetic sequence. So here's what we're going to do. Why don't we do this? Using our formula, let's find the sum of the first 5 terms. Now, n is therefore 5. This is A1, and this is A5. Okay, A1 is 1, A5 is 9. So for this formula, I'll have 5 times 1 plus 9 over 2, 5 times 10 over 2, and that reduces to 25. Or actually, I left out a step. Let's do this one more step. This is 50 halves, 25. And if you go ahead and actually take out your calculator and add these up, you'll see that they do in fact add up to 25. So I don't know about you, but I'd rather do this formula than add them up myself, unless it's just a few terms when you don't really have to worry about it. Well, that wasn't so bad, was it? I think there's another example in here. Let me go see. Yes, there is. Are we ready for it? Oh, no. People are not shouting out yes. I don't know what's going on here, but all right, let's take a look at this one. There we go. I knew it. Yes. We need the sum of the first 6 terms. Oh, no, don't be like that. This stuff is amazing. It's not just okay, it's amazing. We all have to be aware of if it's amazingness, if there is such a word. But anyway, 6, exciting. Oh, all right. Well, you know what? That's okay. We can take care of the confusion. If you're not excited, well, I don't know what we can do about that. Okay. So let's take a look at this one. We're going to get the 6 for 6 using this amazing little formula. All right. Now, this is your challenge. Let's see what you can do. And you can see you could do, go ahead, add them up if you want to. But this will be a little quicker, I think. Remember, so 6, we're looking for 6. Oh, we're looking for this. We're just arbitrarily choosing the 6th term. Let's say there's some reason why we need to know. Let's say that there's 6 people who've donated this money to the math club. Oh, I like that. Is there a math club at Sony Purchase? And we want to know how much money we got, so we can figure out how to budget it. Okay, well then we'll add up the first 6. So, oh, here we go. Oh, somebody's got it. Oh, you're so close. Almost. Close, but no cigar. You know what they say, close only counts in horseshoes. What does that mean? You ever heard that saying? Why do we say that about horseshoes? Has anyone in this room ever actually played horseshoes? Yeah, there's a big stick. Yes. Yes, good. Why do we say close only counts in horseshoes? Because if your horseshoe gets within one full horseshoe of the stake, you get points. Well, it can be fun. As long as you don't throw the horseshoe in the woods. I mean, 78. Yes, somebody has the right answer. It is, in fact, 78. Let's see why. No, even worse. No, not at somebody. No, those things weigh a ton. But you can get you can get those rubbery plastic ones just in case. Anyway, so you get 6 for N. This is A1. This is A6. So it's 8 plus 18 over 2. So then you have 156 over 2, 78. And now if you go ahead and add them up, you'll see that it is in fact 78. You don't have to, but you can.
I'm a little confused.
Okay, go ahead.
So the six, are you? I'm just a little confused where you're getting the six from. Is that because
Oh, I
you're
just completely randomly chose the 6. Like, suppose that for some reason we need to know the sum of the first 6 terms. Um,
okay?
that part was complete. I could have just as easily asked for the first 4 or the first 3 or the first 7. That has to be given to you in the problem. Okay. There's no specific reason for it.
And so when you're doing, sorry, I don't mean to
Go
interrupt.
ahead.
When you're doing 8 plus 18 over 2, you're not taking into the six while
The
doing.
6 comes here.
Okay. Okay. Thank you.
Well, in a minute, we're going to see with our historical example why this formula works. Okay, maybe that'll help when you see what it's all about. So what I would like to do too, remember earlier I showed off my knowledge of this formula by giving you 1 through 10. Let's check that one out. How did I know that the sum of the first 10 was 55? Okay, well, let's find out. Because in a case like that, you would have S10 is 10 times 1 plus 10 over 2. So in other words, I did not add these up in my head. I know this formula. And so the sum of the first 10 integers is 55, or the first 10 natural numbers. Now, that leads us up to a wonderful historical anecdote from math history. We're going to introduce you to a very famous mathematician from the 18th century. Here he is, Carl Gauss. Now, of course, he's one of the great mathematicians in history. It was obvious at an early age that he was a genius. Okay, often with these people, it's noticeable from a very young age that they're really good at something. Okay, so not always. Sometimes some of these guys develop very late. Like Einstein, apparently it was not obvious at all for many years that he was a genius, but oh, it was with Gauss. And so what happened was, this is the story. One day, when he was in elementary school, the teacher decided it would be fun to have a contest with the children in the class. And she said, all right, everyone, take out a piece of paper and add up the numbers from 1 to 100. Now, clearly, those numbers represent an arithmetic sequence. So here's what happened. Now, you can imagine they're all little kids. They take out their paper, they're all excited. there's a prize apparently for whoever wins this, gets there first. And they're like writing them down and writing numbers, and they're writing like crazy. And all of a sudden, in a matter of like a minute or two, Carl comes up to the teacher's desk and says, "Teacher, it's just 50-50, isn't it?" She says, "Carl, how in the world did you figure that out?" He says, "Well, look, I wrote them all out and I noticed something interesting. If I take 1 and 100, they add up to 101. If I take 2 and 99, they add up to 101. If I take 3 and 98, they add up to 101. And so on and so on. So we have 50 pairs of numbers with a sum of 101. So the total must be 50 times 101. Now, we can confirm this with our formula, if you like. Watch this. So you've got S100 equals 100 times 1 plus 100 over 2. These cancel out. 50, 101. And that's all it is. So it's basically nothing but the first and the last number, add them up. We have that many pairs, and therefore the sum is n times that. Now that's impressive for us. Imagine if you were in elementary school and you came up with this idea all on your own. Would you agree that this child has a bright future in math? Oh, yes, he does. Okay, it's kind of like, remember Mozart playing concertos when he's 4 years old or whatever it was. Yes, it's obvious at a young age that this guy has something on the ball. Yes. Anyway, so now it's time to move on to the second kind of sequence, which is called the geometric sequences. These are a little bit different because instead of having a constant difference, they have what's called a constant ratio or multiplier. So let me show you what I mean by that. So here, these are clearly not arithmetic because they grow much too quickly, don't they? But if you look at these carefully, you'll see here I'm constantly multiplying each term by 2 to get to the next one. So we say that the ratio, the common ratio, which we're going to call R, is 2. Down here, what's the common ratio? 3. And how about in this last case? What's the common ratio? 5. Yes, that's right. It was 5, exactly. Now, I do want to point out that the ratio doesn't have to be a positive integer. What if I had something like this? What's the common ratio in that case? Yes. Well, it's not actually 2, it's 1/2, because you're multiplying each of the terms by a half to get to the next term. Exactly. It's a half. Okay. In other words, to go from here to here, I multiplied 1 by a half. Here I multiplied a half by a half, a quarter by a half, et cetera, et cetera. Now, here's another interesting case. Watch this one. Oops, wait, no, I screwed it up. Sorry. Oh, we have somebody who knows. It's -2. That's right. -2. That's how come the signs keep going back and forth. It's negative. So all of these are possibilities. As long as they're all being multiplied, that makes it a geometric sequence. Now, just like before, we need to be able to figure out a particular term in a geometric sequence, here's the formula. Now you notice there's no D in here, but we do have an R, the common ratio. And of course, n is the term that we're looking for. This is the nth term. And this one is the first term. Well, why don't we do some examples? I think you'll agree that examples are the way to go. Practice makes perfect. That's right. Some of you are musicians and you know what I'm talking about. Can you get good at the piano without ever playing it? No. All right. Oh, here we go. Let's try this one. All right. So here's your formula. Now you could write this out. Now, first things first, notice that the common ratio is 2. So with that being said, why don't you figure out for me, oh, you've already got it. Oh my God. Is it 64? That sounds right. Let's try it. 32. 1, 2, 3, 4, 5, 6. Yes. Anyway, somebody else has it too, I can see. 64. Now, you can see by writing them out, but let's use the formula. Our A1 is 1. The common ratio is 2. We're looking for the 7th term. This reduces to 2 to the 6th, which if you go to your calculator, you'll see is in fact 64. Nice. They're the same thing. All right. That was easy. Well, in fact, it's surprisingly easy considering that it's a geometric sequence. All right, now let's see if there's another example here. Oh, let's try this one. Oh, I think we have a winner. 243, exactly. So here the common ratio is 3. So you can tell just by looking at these, the next one would be 243, good. But with the formula, A5 is A1, which is 3, times 3 again, raised to the 5 minus 1 power. Now here there's an implicit 1 in the exponent. So this is 3 to the 1 plus 4, 3 to the 5th. And if you put that in your calculator, you'll see that it is in fact 243. And that's it. That's all you have to do. Now, of course, you probably can guess what's coming next. Use your psychic powers and tell me what's coming next. Yeah, more math, but I mean specifically, we did 2 things with the arithmetic sequences, and we only did one of them. Here, what's still left to come? How about the sum of the first n terms? Yeah, that's correct. The sum. We still don't have a sum formula. Well, let's get it. There we go. Now, it looks a little intimidating, but of course it's not, because we know what all these terms mean. We only need the first term, r to the nth power here, just plain 1 minus r here. And this will work very well. All right, let's try this. So let's say that we're looking for the sum of the first 4 terms here. Okay, so I want to know S4. And don't forget, the common ratio here is 2. A1 is 5. So plug that in and let's see what you get. So I plugged them in for you. What comes next? 5 times 1 minus 32. Oh, wait a minute. No, did I do something wrong? No, sorry. It's the 4th term. My fault. Hold on 1 second. This is a 4. The 4th term, sorry. Yes. So instead, we'll have 5 times 1 minus 16. So 5 times minus 15. Up, we have somebody who knows. It's, because I want I should have written it down here. Find the sum of the first 4 terms. Okay, that's why n is 4. Anyway, so the negatives cancel out and we end up with 75. And if you add these 4 together, you'll see that they do in fact add up to 75. So that wasn't too bad, considering. All right. I think there might be another one waiting for us. Well, yeah, that's true for 4. What if we needed the first 40? Oh no, now we're talking formula time. That's right. But yeah, no, sure. For 4, you sure just add them up in your head. I mean, really. But for a large number, yes, this starts to become more and more useful. So let's see. Was there one more? Oh, sadly enough, that was the last example. That's right. We're going to have plenty of examples now. Why am I saying that? Before I completely forget, now we got a few minutes. I'd like to take a peek at chapter 6. But before I do that, I just want to remind you that we're now ready for the 3rd problem set in chapter 5, which is on Moodle as we speak. Let's go find it. And when you look at it, you'll say, you know what? This is going to take a long time. And you're right. But by the time you're done, you'll be good at this stuff. And I mean good. Wow, 55 questions. Ooh, and not only that, but there's even word problems in here. So we're going to do these on Monday. Now, under the circumstances, since you'll probably be snowed in anyway, that gives you a lot of time to get this ready, doesn't it? Yes. In fact, you'll probably do this before anything else, won't you? Not Sunday night, I bet. Well, it doesn't matter, does it, when you do this, as long as it gets done, because this is where you'll get practice. And by the way, I think I've mentioned this before, the exam, when it finally shows up, will be very much like what you're seeing here. So when you do these problem sets, you are simultaneously studying for the next exam. So you're getting 2 for 1. Each hour of working on problem sets is an hour that you're studying for the next test. How cool is that? All right, anyway, so why don't we now get out 6? We're just barely going to start it. It's kind of an extension of 5, but with some interesting twists along the way. So in the beginning part of this chapter, we're just going to be looking at some very basic concepts that you've probably seen before, a few vocabulary words, not much more. And then we can dive into it more deeply next week after we're finished with that problem set. All right. The problem set might take up all of Monday. I don't know. I remember in the past, it did take up a long time, but that's all right. There's no rush. Is anyone in a desperate hurry to take an exam? No, I was kind of pretty sure about that. Have you had any yet in your other classes? Or are they coming up? No, maybe. I don't know. The good thing about this online business is that you have to do it at home, don't you? I can't call you into the classroom and say, here's your test. It doesn't work like that at the moment. In fact, it may not work like that again for a while. I don't know. The way things are going, you do already. Ooh. So if we take our sweet time getting to our exam, that won't be a problem. No, I thought so. Anyway, let's look at this real fast. We're gonna start by looking at techniques for simplifying expressions, algebraic expressions, as well as evaluating them, which means providing them with a specific value. And of course, as always, whenever we have any kind of results in math, our job is to make them as simple as possible. In math, simple is good. Just like in life, simple is good, isn't it? Do you like your life being simple or complicated? Oh, I bet I know what the answer is. Simple is good. We don't like complications. Simple, yes, always simple. Complications suck up all of your energy. We don't like complications. All right. Anyway, so let's start here. A variable, of course, is a quantity that can change, like X or Y. We almost always use X or Y to represent variables. I don't know how that came to be. There's apparently an element of mystery associated with X, and therefore it makes sense that X should be a variable. An algebraic expression is a combination of variables, constants, and operations, which of course includes multiplication and division. And that's right. Every pirate book you ever read as a child had X's where you can find the treasure. That's right. There's always been a element of mystery. In fact, somebody should write a book about that. The Mysteries of X. I bet it would be a big bestseller. Because you know, the demand for math books is insatiable. No, I shouldn't say that, because periodically you do see math bestsellers in the New York Times. It does happen. The X-Files, that's right. Why would they call it? They wouldn't call it the R-Files, for God's sake. It's the X-Files. There's an element of mystery about it. X is mysterious. Okay. I don't know if anyone knows why, but we've always associated X with mystery. Anyway, or X-Men. Ooh, I thought of that one myself. X-Men. You all read those comics? Wolverine and those guys? X-Men. It would have been pretty weak to call them the B-Men. It just isn't the same. Yeah, that's right. Pretty cool, huh? Anyway, so and then a coefficient is simply a constant that appears in the term of an algebraic expression. So we're going to look at some examples now. Let's do one right here. Now, it's referred to as an expression because it isn't set equal to something. Like if I set this equal to a constant, it becomes an equation. Right now, the way it stands, this is only an expression. And you can see I've got a constant here. All right, hold on a second. A constant. I have an operator. I have a variable. I have an exponent, and I have a coefficient. Okay, and so I got them all in there, didn't I? And that's what we'll refer to from now on as either an expression or an algebraic expression. All right, now let's look at some actual examples. Okay, other examples, I mean. Okay, how about this one? And you can see, by the way, this is a good point to remember that when you have something like this, there's an implied coefficient of 1 here. It isn't specifically written down, but it's understood that you can think of this as 1 times x squared. Same thing with this. If you got x by itself, there's an implied exponent of 1. So like before, we've got a lot going on here. We've got coefficients, we've got exponents, we've got operators. The pluses are operators, and we have exponents. Okay, now, in about a minute, we're going to reintroduce an old friend of ours. And that friend is the distributive property, specifically distributive property of multiplication over addition. All right, what do I mean by that? Oh, that's right. Remember, if I have something like this, I'm going to multiply this constant by each of these terms, and then I'm going to add them together. So I've got 3x plus 3 times 2y, or 3x plus 6y. In the second case, I have to be very careful with this negative. I've got negative 8x. Well, first, I have negative 4 times 2x minus 4 times negative y. So I ultimately end up with negative 8x plus 4y. I'm getting a little stretchy here. All right, here we go. Oh, all right, let me leave that, put that back in case you're not done. So then what we're going to do is remember that we want to simplify our results whenever possible. In the case of algebraic expressions, we don't have a lot of, we have a mixture of numbers and variables and all the rest. So it's not always possible to do that. But the strategy there is to combine what we call like elements. And so in other words, whenever there's multiple terms involving, let's say, x, and there's constants floating around, we always want to bring them together and create a new expression which essentially consolidates them all and makes it simpler. For example, what about this one? Would you leave it, if you had an answer like this, would you just leave it like that? No, because you can combine the 3x and the negative 5x. Yes, you will. So what we can do is recognize they have a common factor of x, consolidate them, and before you know it, you've got negative 2x plus 2. Instead of this. And I think you'll agree that the second one is easier or simpler than the first one. And it's like, why would you want to leave the term separate like that anyway? So how about this one? It's a little bit more complicated. What's happening here is that you've got these that belong together. These are like terms, and so are these. The constant here is just off by itself. We don't need to do anything with that one. So we've got 3 plus 1. Remember, there's an implied 1 here. These are our x squares. For the x's, we have 8 and -2. And so when all the dust settles, we have 4x squared plus 6x plus 5. And that's as simple as we can get it. All right, are we ready? Let's try another one. This one's a little bit trickier because there's x cubes involved. Oh my God, look how complicated this is getting. Not really. We've got the 2x cubes. We can consolidate them. We have the x squares. And again, remember there's an implied 1 here. And so the bottom line is this is the same as minus 3x cubed plus 9x squared plus 3. All right, I'll tell you what. Now you've got a big assignment ahead of you. Not to be collected, of course, but you've got to crank it out between now and Monday. There's a lot of questions there, as you saw. And you don't want to wait till 9 o'clock on Sunday night, do you? I don't think it's a good idea. You can work on a Monday morning, but you probably are getting up at 10:28 anyway for a 10:30 class. Is that about the size of it? Since your bed is right next to your computer, you're putting that to good use, aren't you? There's no commuting, so you just sort of hope that your hair looks okay, and you just sit in front of the computer. All right, so yes, so don't forget about that. Chapter 5, problem set number 3, we'll be going over that on Monday. It probably will swallow up the whole day, but once we're through with that, we can carry on with 6. Now, down the road, there'll be a problem set for 6, and then there's going to be what we call a sample midterm, which is a review. Think of it as a dress rehearsal for the actual midterm, which is based on chapters 5 and 6 only. And that probably won't show up until, let's say, maybe the first week of March. So we have time, but we have to know where we're going to. And so that's where we're headed. But so the midterm should not get in the way of your other classes anyway, because it'll be a little later, I'm guessing, than your other classes. Anyway, so I guess that's enough fun for one day. If you were planning on going anywhere today, that's out the window. That's for sure. So if you look out there, you'll see why. But, just do what you have to do to survive. So are you allowed to go visit each other in the other dorms? You're not? Oh my God. Well, that must be depressing. How about the people on the same floor? Same building? That's okay. I always wonder how that works. Oh no. Oh boy. So you're sort of stuck in your room by yourself? Oh, that can't be good. What if you don't have any roommates? What do you do now? Ouch. Well, I mean, no, but you have to eat, don't you? How do they figure that one out? Or how do you eat in a situation like this? You don't all have kitchens in your rooms. There's got to be some place you can go eat, isn't there? Oh, so you're allowed to go in there, but you can't sit next to anyone?
But I think it's takeout only.
Oh, I get it. You bring food back to your rooms. Okay. All right. Boy, that is really depressing. Man. All right. I kind of wondered how they were handling that. But all right. Anyway, enough depressing talk. Let's think about math and how exciting it is and how much fun we had with it today. And don't forget about Carl Gauss. He should inspire you with your math studies. If you want to be the next Carl Gauss, you have to study the stuff every day. Don't forget about that. All right. So I'll see you all then, hopefully on a happier Monday than what's going on today here. All right. See you then. All right. Bye.
Thank you.
Okay. You're welcome. Okay. Bye.
Thanks.
Okay. See you later.